Welcome. This is a walkthrough of the exercises we did today in Data 1010. We're starting the course by doing some introductory programming exercises in Julia. We're going to use Julia extensively in the course, and if you're familiar with Python or R, then you'll find Julia to be pretty familiar. This is an example of the harmonic function coded up in Julia. So that's the function which sums the first so many positive integer reciprocals. And the way this function works is that we start with a value s at 0, and then we loop through the first n positive integers and add their reciprocals to s, and then we return the value of s on the last line. And unlike in Python, a function will return the value on the last line without a return keyword, and it's customary to omit it. So we can define the function, and then we can run it with an input of 10 million, so it's going to be summing 10 million integer reciprocals. And it takes about a tenth of a second. And notice that we use this at time object here. This is called a macro. And a macro in Julia is a function that takes in code rather than an actual value. So it's looking at this whole piece of code and doing something with it, in this case running it repeatedly so that it can be accurately timed. In Python, you can write a function that looks very similar, as shown by these lines, but it takes much longer to run. So what we're doing here is calling Python from inside of Julia. We use a pycall package for that, which we import with using pycall. And we can write Python code. We can write multi-line Python code with a triple quoted string prefixed with pi, and we can return a value of an expression by using a single quoted string with also with prefix pi. So what you'll see is that the Python code takes longer to run, and you're going to get very similar results if you run it in an actual Python interpreter. So the time that this takes really is in the interpreter making this loop, this for loop here. Julia does not actually execute that for loop in the Julia code. What it does is it compiles it down to machine code and hands that to the processor. So it's performing that calculation in essentially the same way that C or some other compiled language would. And in fact, you can see exactly the machine code that's being, actually this is assembly, you can see the code that's being handed to the processor though, and there's not that much of it. It's not super readable, but you can see that there's only so many lines here. And this can be a useful macro to use in general if you have a pretty simple function and you think you might have done something that caused the compiler to have to do too much work. You can run code native and see if there's some very large number of lines here, and in that case that's an indication maybe you can simplify things. The flip side of the way that Julia works is that every time you call a function for the first time in your given session, it has to be compiled, and that takes more time typically than it would take to just run the function in Python or R. So the speed up comes from running the same function many times, which is very common in numerical computing, but sometimes there are things that feel less snappy for that reason, particularly if you're loading packages, like especially the plotting package has really a lot of functions that have to be compiled. And that happens every time you start a new session, so just prepare for that. So let's get into the exercises. So the first thing to note here is that there are quite a few small differences in syntax and function names and design patterns between Python and Julia. So what you want to do is open up a window to this Julia Python R cheat sheet, which is kind of a Rosetta Stone between the different languages, and there are quite a few common patterns here which are demonstrated in parallel in those three languages. So in particular, we're going to be focused on Python and Julia here. So the first exercise is to write a function which takes a single parameter n and outputs an n by n matrix that looks like this. It's got 2's along the main diagonal, and then it's got -1's on the off diagonal. So we want to write a function. We've seen an example of that. Let's just look at it over here. So here it is on this panel, functions. So it's the function keyword that we're going to use to define a function, followed by the function name, and then a list of the parameters. And the block is going to be delimited with an end here. And we just write our function body in between those two. Notice there's no colon like in Python. Also, unlike Python, and also unlike Python, the indentation doesn't really matter. You should do it because it looks nicer, but it doesn't affect the semantics of the language. So, okay, so let's define a function called string of n. And since this matrix has a lot of zeros, let's start by defining it to be a matrix of zeros that's n by n. And this works the same as in NumPy, but if you didn't know that, you could look at the cheat sheet and you could look at the cheat sheet and find it somewhere. So vectors and matrices. So if you want to fill a matrix with a particular number, you can use this fill function. In NumPy, it's numpy.full, and then it's not actually on the cheat sheet, but zeros and ones, both in NumPy and in Julia, are kind of shorthands for filling with zeros or with ones, since those use cases come up quite a bit. So if you use fill for this, that's fine as well. So anyway, now we have a matrix of zeros. So we need to correct the diagonal entry. So let's just do that in a simple way by making loops. So for I in the range from 1 to n, we're going to take the I comma ith entry of A and assign 1 to it. Sorry, 2, should be 2. And then we need to set the off diagonal entries, and one simple way to think about that is we start with the second entry here, and the entry above it and to the left of it we fill in -1s, and then we just go down the diagonal and continue to do that. The one above, the one to the left, both make them -1. We get into the corner, we put down the last two -1, and that's it. Last two -1s, and that's it. So I is going to go from 2 to n, and we're going to set I comma I minus 1 to -1, and we're going to set I minus 1 comma I to -1. And that's it. We've got our matrix with -1s in it, with the 2's in it, and all the rest are zeros. So we're just going to return that matrix on the last row. So you can see just by checking a small example that it does what we're asking it to do. Okay, let's move on to exercise 2. So we're considering a random symmetric matrix that just has uniform random entries along the diagonal and above the diagonal, and then below the diagonal it's just copied. The values are just copied so that the matrix is symmetric. The details here don't matter that much. The point is just it's a random symmetric matrix. And what we're told is we're supposed to start with a vector v0 that's 1 in the first position and 0 in the rest of the positions, and then repeatedly apply a to that vector and then divide by the norm so that we get a unit vector. And the problem statement is telling us that as we repeat that process over and over again, then what we're going to get in the long run is an eigenvector with whose eigenvalue was the largest in absolute value. So let's just program this iteration just like it's written in the math language, just translate that to code. So in order to test it, let's copy the code that was given. So now A is going to be a matrix that is defined in this cell to be a random symmetric matrix, and now we can define a function. So let's call it lead eigenvector, and it's going to take a matrix A as a parameter because we're computing an eigenvector of A. And so we're just going to follow the instructions. So we want V to be a vector which starts with 1 and then has a bunch of zeros. Probably the most straightforward way to do that is make it a vector of zeros and then fill in the first value to be 1, like that. And n here is supposed to be the length of the vector, so we need to say what that is. And the way that you get the size of a matrix in Julia is with the size function. So you can just do size of A, and that gives you a tuple of the dimensions of A, or you can supply a second argument here which says which axis we're talking about. And if we're computing eigenvalues, it's a square matrix, so we can just grab the first one. So what we're going to do, each of these updates is going to calculate A times V and then divide by the norm of A times V. So we just write that, and we need to do this repeatedly so we can put it in a for loop. For I in 1 to, let's just say 100, if you were going to put this into a library for people to use, you'd want to do it in a more principled way, but we're just experimenting here. And at the end, we're going to return the vector V. And oh yeah, we need to store the result when we compute A times V. And we're going to store it to the same variable so that we don't have to keep up with the history of how this iteration evolves. We could do that. We could make an array of vectors and push into that array the new values, sort of grow the array as k goes from, sorry, call it I, as k goes from 1 to 100. But we don't care about the intermediate values, we just care about the value at the end. So we can save some memory by just reusing this variable v and assigning to it again. So we return v at the end, and we can check that our code worked by comparing it to the function called eigen from Julia. So that's in linear algebra, so we import the linear algebra package, which is part of the standard library, so that comes with any Julia installation. And it's really just separated out because that way, if you don't need it, your Julia session will load a little bit faster. But you can definitely rely on everything in this package as much as you want to. Okay, so we want to just compare. So we can compute eigen of A and see what that gives us. And the eigenvalues are here. We see that the largest eigenvalue is the largest eigenvalue is 5.6, and that corresponds to the last eigenvector. So this last column is the one that V should be close to. And we can just check that. So we can do lead eigenvector of A and see what that looks like. And sure enough, this vector is the same as this one at the end, except for a sign of -1, and that's just intrinsic to eigenvectors. So if you have a unit length eigenvector, it's always the case that -1 times that eigenvector is also an eigenvector. So the sign here for each of these columns is arbitrary, and so that doesn't match, but otherwise it's clearly what we did worked here. Okay, so the next section is on pointwise operations, also known as broadcasting. And this is actually a very important part of the design of NumPy, and it's important in Julia as well, although not quite as important. And the syntax is a bit different, so it's worth going over. So this is Python code. We're importing NumPy, and we just define a little matrix 1, 2, 3, 4. And if you do use the asterisk in Python between two NumPy arrays, it's going to apply that pointwise. So each one of these entries, 1, 2, 3, 4, gets multiplied by the corresponding entry in the matrix that it's being multiplied by, which is A again. So in effect, each of these entries is just being squared, and that's what you can see here. But in Julia, if you want to achieve the same effect, then you need to put a dot in front of the asterisk. So if we run this in Python and we run this in Julia, we get the same effect. If we just use a regular asterisk, then we're going to get regular matrix multiplication. So if you square that matrix out, this is what you're going to get. If you want it to be pointwise, you put a dot. And that's true throughout Julia. The dot modifies an operation so that instead of performing its standard mathematical meaning, it's going to perform operations element by element. So for example, if you have a function f and you want to sort of map it over a list, one way to do that is just do f dot and then supply your array, and that's going to return an array where f has been applied to each of those values. So let's take a look at an example of that. We're going to plot the function sine squared x plus 1 over the interval from 0 to 2 pi. We already have x here for us, so this range function is another way of generating a range object other than using a colon, and it allows you to specify exactly how many entries you want in that array. So what we want to do is take that array x and compute sine squared of each of its entries and add 1 to it. And those are all pointwise operations. We want to do sine squared of a value plus 1 for each value separately. So it's going to be sine. So if we do sine of x, that won't work because that's actually taking the whole array and trying to plug it into a sine function. What we need to do is sine dot of x, and that'll compute the sine of each element individually. And then we square with dot squared, and then we add 1 with dot plus 1. And then we can plot this. And it's going to take a while to load up because, as I said, plots has a lot of code to precompile. But okay, that actually wasn't too bad. So we got our plot. So mission accomplished. So the next section is on multiple dispatch, which gets into Julia's type system. So we're not going to go too far in that direction, but it's an important thing for purposes of understanding error statements when you're debugging to have a little bit of awareness of this. So we're just going to do a couple of examples. So the idea of multiple dispatch starts with the observation that in math we use the same notation even when what's happening is only analogous and not exactly the same thing. For example, you use this central dot to just denote regular real number multiplication, but also to denote the dot product between two vectors. And in further math, there would be even more advanced objects that you might want to use this dot operation for. And in each case, you'd be just defining some new operation. It isn't as though the dot has some essence that you're always tapping into. It's just a piece of syntax that's getting reused over and over again for different purposes. And hopefully those different purposes are analogous, but ultimately, as the author, you have to create that meaning. And Julia has an analogous piece of functionality, which is that you can define two functions. You can write two function definition statements. And what that does is it creates what are called two methods for this function. So you see when we run this cell, it tells us that my dot is a generic function with two methods. So the idea is that my dot is one thing, it's a function, but it now has two different pieces of data associated with it that help it evaluate its arguments. So if the two arguments being supplied to the function are both real numbers, then this method will get used and the numbers will just be multiplied together. If the two objects that are fed to this function are both vectors, then what we're going to do is zip those vectors together, so that creates essentially a list of corresponding pairs, and we're going to multiply them in pairs. So we loop over the elements of v and w in pairs, and then we multiply them and then add up the results. So that's a normal dot product. We could actually have used c dot for this, like v backslash c dot tab gives you the actual c dot. This would also have worked, but just to spell it out explicitly, we wrote it this way instead. Anyway, to see this in action, call my dot of 2 comma 3 and it returns 6. That's regular multiplication. We can also call my dot on these two vectors and it uses that second method and returns a dot product. So this is called multiple dispatch, the idea being that when you call a function, it's dispatched to the proper method depending on the types of the arguments. And you can notice here that we specified types with double colon and then the name of the type. So real represents a real number that could be an integer or a floating point number with a decimal in it. And then vector, of course, refers to a vector. So the types in Julia are not special. You can create your own types. The types are defined in Julia itself, and they're treated very much the same as the ones that you create. So you should feel very much at liberty to simplify your code by defining objects that represent the mathematical objects that you want to deal with in your code. So for example, if you needed to deal with a bunch of lines of the form y equals mx plus b, you might define a new type called line, which has a slope and an intercept, and you name those two things, for example, slope and intercept. And the way that you define a new type is with the keyword struct. So, for example, if you define line to be a struct consisting of slope and intercept, then you can call line of 1 comma 2, and that assigns 1 to the slope value and 2 to the intercept value. And then you can access those values with this dot syntax. So that looks very much like Python. It's like an attribute in Python. So L dot slope, in this case, will return 1. L dot intercept will return 2. And with this newly defined type that we made, we can write a function that operates on objects of that type and compute some values we're interested in. Like, for example, if we want to know the intersection point of two lines L and M, then then we can solve this equation y equals m1x plus b1, y equals m2x plus b2 for x, and we get this solution for x. And then of course, once we have that value for x, we can plug back into either of these equations and get the corresponding value for y. So we can just write that code here. We can say x is minus, and then b2 represents the intercept of the second line, so that's going to be m dot intercept minus L dot intercept divided by the slope differences, which is m dot slope minus L dot slope. And then once we have that x value, then y is just let's say L dot slope times x plus L dot intercept. And then we're just going to return x comma y. And let's uncomment this assertion statement to check that this all works. And it's all good. If this statement had been false, the assert would have thrown an error. We can delete assert to see that this actually does return true. Alright, so finally we're going to take a look at some plotting, and specifically we've got this figure to try to reproduce. And we're going to look over at the plots.jl cheat sheet to try to see what sort of visualization this is. So it's not like a line graph or a scatter graph. So let's take a look. We're going to see the main plot types here in this first panel. And this looks like a heat map. And the way plots.jl works is it takes the data as arguments and then plot attributes, which are enumerated over here as keyword arguments. So let's try to get the data right first. So we're going to use heat map, and so it's going to be, as it explains it here in the hint, x is going to be a vector of x values, y is going to be a vector of y values, and z is going to be a two-dimensional array storing the values that correspond to these colors. And so clearly the x value is going from minus 10 to 10, the y value is going from minus 10 to 10. And to make a multi-dimensional array, the easiest way to do it in Julia is to use this multi-dimensional array syntax. So we're going to have x ranging from minus 10 to 10, y ranging from minus 10 to 10, and we just need to put something here to generate the actual values that are being plotted. And we have a lot of advice for that coming from this color bar. So we can see at the middle it's 0 because that's the darkest color on the color bar and also on the figure. And then it increases from 0 as you move away, and it reaches 200 around the edges. And we can tell that just based on looking at this picture that the level lines are going to be circles that are centered at the origin. So that suggests some sort of x squared plus y squared type function. And in fact, x squared plus y squared itself is 200 when both values are 10. So that's going to be just right. And so the figure didn't quite match up because it's spread out horizontally a little bit. And the way to fix that, if we look back over at the cheat sheet, is right here, aspect ratio. So if we set the ratio to be, let's try equal, then it should do what we want. And that's much better. So this bit in the middle here is a square, and the color bar matches. Not sure why there's this extra space on the side here, but this is close enough. And this last exercise is a bit more challenging than the other ones. I put it here for fun, and I'm not going to cover it in this video.